You think you live in three dimensions: length, width, height. You move through space in three directions. You exist as a three-dimensional being in a three-dimensional universe, solid, real, tangible. But what if I told you that's an illusion? What if the three-dimensional reality you experience is actually a projection from a two-dimensional surface? Like a hologram where a flat image contains all the information needed to reconstruct a three-dimensional picture. What if everything you see, every particle, every force, every structure in the universe is encoded on a distant two-dimensional boundary, and the three-dimensional space you think you occupy doesn't fundamentally exist? It's emergent, reconstructed from information on that boundary. I'm Leonard Susskind, and I helped develop the holographic principle in the 1990s. And I'm going to tell you why some of the best physicists in the world now believe the universe is a hologram. Not metaphorically, not as a loose analogy, but as a precise mathematical statement about the structure of reality itself. Let me start with the problem that led to this idea: black holes. In the 1970s, Stephen Hawking discovered something disturbing about black holes. He showed that black holes have entropy. Entropy is a measure of information, the number of microstates consistent with a macroscopic description. For ordinary matter, entropy is proportional to volume. A box twice as big has twice as much entropy. But black holes are different. In 1973, Jacob Bekenstein proposed that black hole entropy is proportional to surface area, the area of the event horizon, not the volume inside. Hawking's calculation confirmed this. The entropy of a black hole equals 1/4 of its horizon area, measured in Planck units. This is the Bekenstein-Hawking entropy formula, and it's bizarre. Why should the information content of a black hole depend on area rather than volume? At first, physicists thought this was just a peculiarity of black holes, some strange feature of horizons. But then Gerard Hooft and I independently started thinking about what this really meant. If the maximum entropy in any region is proportional to the surface area bounding that region, not the volume, then something profound is happening. It suggests that the fundamental degrees of freedom, the basic units of information in the universe, don't live in the volume. They live on the boundary. The three-dimensional space we experience is somehow encoded on a two-dimensional surface. This is the holographic principle. And if it's true, it means reality has one less dimension than it appears to have. Now, you might think this is just a theoretical curiosity. Interesting math, but nothing to do with reality. But then in 1997, Juan Maldacena made a discovery that changed everything. He found an exact mathematical realization of the holographic principle. He discovered a duality, a precise equivalence between two theories. One theory describes quantum gravity in a space called anti-de Sitter space, ADS for short. This is a space with negative curvature, like a saddle shape. The other theory is a quantum field theory without gravity living on the boundary of that space. The boundary has one less dimension. If the bulk space has three spatial dimensions, the boundary has two. And here's the remarkable thing. These two theories are exactly the same. Every calculation you do in the gravitational theory gives the same answer as the corresponding calculation in the boundary theory. They're two descriptions of the same physics. This is called the ADS-CFT correspondence. CFT stands for conformal field theory, the type of quantum theory living on the boundary. And this correspondence is not approximate. It's exact. It's been tested in thousands of calculations, and it always works. What this means is stunning. A universe with gravity in three spatial dimensions is exactly equivalent to a quantum theory without gravity in two spatial dimensions. The three-dimensional universe is holographic. All the information describing it is encoded on its two-dimensional boundary. Everything happening in the bulk, particles moving, fields fluctuating, black holes forming. All of it is encoded in the boundary theory. The bulk is emergent. It's reconstructed from the boundary information through quantum entanglement. Now, our universe doesn't have a negative cosmological constant. We live in a de Sitter space with positive curvature, not anti-de Sitter. So add CFT doesn't directly describe our universe. But the fact that holography works exactly in even one case suggests it's a fundamental principle. And many physicists believe a similar holographic description exists for our universe. We just haven't figured out the details yet. The basic idea is that there's a cosmic horizon, the edge of the observable universe, and all the information about our universe is encoded on that horizon. We think we're three-dimensional beings living in three-dimensional space, but fundamentally, we're patterns of information on a two-dimensional surface, projecting the illusion of three dimensions. Let me explain what this means more concretely. Think about a hologram, an actual hologram like on a credit card. It's a flat piece of plastic with interference patterns on it. When you shine light through it, you see a three-dimensional image. The image has depth. You can look around objects, but all the information creating that three-dimensional image is stored in the two-dimensional pattern on the plastic. Nothing is actually three-dimensional. The depth is reconstructed by your brain from the two-dimensional data. The holographic principle says the universe works the same way. The information describing you, your atoms, your thoughts, your entire body is encoded on a distant two-dimensional surface, the cosmic horizon, and the three-dimensional you is reconstructed from that information. You're a projection. Now this sounds insane. How can I be a projection from a surface billions of light years away? How can my thoughts, which feel so immediate and local, be encoded on some distant boundary? The answer involves quantum entanglement. Entanglement is the phenomenon where quantum systems become correlated in ways that can't be explained classically. When particles are entangled, measuring one instantly affects the other regardless of distance. Einstein called it spooky action at a distance. In the holographic picture, entanglement is what connects the boundary to the bulk. The boundary theory has many degrees of freedom that are highly entangled. And this entanglement pattern creates the illusion of three-dimensional space. Regions of the boundary that are strongly entangled correspond to nearby regions in the bulk. Regions that are weakly entangled correspond to distant regions. Space itself emerges from entanglement. This is not just philosophy. Shinzei Ryu and Tadashi Takayanagi proved in 2006 that in AD-CFT, the entanglement entropy of a region on the boundary equals the area of a minimal surface in the bulk connecting that region. This is the Ryu-Takayanagi formula. It's an exact mathematical relationship. What it tells us is that space-time geometry is encoded in entanglement. The shape of space, the distances between points, the curvature, all of this comes from quantum entanglement patterns in the boundary theory. Without entanglement, there is no space. Mark van Ramsdonk took this further. He showed that if you remove entanglement between parts of the boundary, the bulk space-time tears apart. Entanglement doesn't just correlate with geometry, it creates it. This is revolutionary. Space is not fundamental. Space is emergent from quantum information. Let me tell you what this means for the nature of reality. If the holographic principle is correct, then three-dimensional space is an illusion. A very convincing illusion, but an illusion nonetheless. The fundamental reality is two-dimensional. Information encoded on a boundary. And everything you experience, every object, every interaction, every moment of consciousness is a consequence of that information organizing itself according to quantum mechanical rules. You are not a collection of particles in three-dimensional space. You are a pattern of information on a two-dimensional surface manifesting as a three-dimensional structure through entanglement. This isn't mysticism. This is what the mathematics of quantum gravity tells us. Now let's talk about why physicists take this seriously. The holographic principle solves the black hole information paradox. Remember the problem? When matter falls into a black hole, it carries information. When the black hole evaporates through Hawking radiation, where does the information go? If it's destroyed, quantum mechanics is violated. If it's preserved, where is it? The holographic principle answers this. The information is never inside the black hole in the way we thought. The interior of the black hole is an emergent description. The fundamental degrees of freedom live on the horizon. When matter falls in, its information spreads across the horizon. When the black hole evaporates, the information is gradually released in the Hawking radiation in a scrambled form. The information is conserved because it was always on the horizon, never truly inside. This is called black hole complementarity, an idea I developed with colleagues in the 1990s. The principle says that different observers have different but complementary descriptions. An observer falling into a black hole sees the interior, sees themselves crossing the horizon. An observer outside sees the information spread on the horizon and eventually radiate away. These descriptions seem contradictory, but they're not. They're different slices through the same holographic reality. Neither observer can verify both descriptions simultaneously. The hologram shows different images depending on your perspective. And here's something truly strange. If the interior of a black hole is emergent, reconstructed from horizon information, then the interior only exists relative to observers who fall in. For observers who stay outside, the interior never forms. It's not that it's hidden behind the horizon, it's that it doesn't exist in their description. This sounds like philosophy, but it has precise mathematical meaning in ADS-CFT. Let me address the obvious question. If we're holograms, projections from a two-dimensional surface, why do we experience three dimensions so vividly? Why does space feel real? The answer is that the projection is incredibly sophisticated. The hologram is not like a picture on a screen. It's a full quantum reconstruction involving entanglement across enormous numbers of degrees of freedom. Your brain, which is also part of the hologram, processes information in ways that create the subjective experience of three-dimensional space. You can't step outside the hologram to see it's flat. You're part of it. Your experience of three dimensions is generated by the hologram itself. It's like asking why characters in a video game experience their world as three-dimensional. The game is computed on a two-dimensional chip, but the characters, if they were conscious, would experience a three-dimensional world because that's what the computation creates. This raises deep questions about consciousness and observation. If I'm a holographic projection, what does it mean for me to observe something? What is the relationship between the information on the boundary and my subjective experience? These questions touch on the hard problem of consciousness, and honestly, we don't have complete answers. But what we do know is that in the holographic picture, observation is information processing. When you observe something, information flows from the observed system to your brain. That information flow is encoded in the boundary theory as correlations between degrees of freedom. Your conscious experience is what it feels like from the inside to be a particular pattern of information processing occurring in the holographic description. Now let's talk about the cosmic horizon. If our universe is holographic, where is the boundary? The most likely candidate is the cosmic horizon, the boundary of the observable universe. Due to cosmic expansion, there are galaxies so far away that light from them will never reach us. The distance to this horizon is about 46 billion light years. According to the holographic principle, all the information describing our observable universe is encoded on a sphere at this distance. The sphere has an area of roughly 10 to the 123 square Planck lengths. Since each Planck area can encode about 1 bit of information, the total information content of our observable universe is about 10 to the 123 bitses. That's the maximum. And everything in the universe, every particle, every field, every thought is part of that finite amount of information. This has profound implications. It means the universe is fundamentally discrete at the Planck scale. There's a finite amount of information in any region. Space-time, which appears continuous, is emergent from discrete quantum bits. At the deepest level, reality is digital, not analog. It's made of information organized in quantum states. This connects to another idea, the principle that information is the fundamental substance of reality. John Archibald Wheeler called it from bit. Every physical thing derives its existence from information. In the holographic picture, this is literally true. The physical things we experience are reconstructed from information on a boundary. Matter, energy, forces, space, time, all emergent from quantum information. Here's something that troubles people. If we're holograms, are we real? Does the holographic picture mean we're illusions, simulations, not genuinely existing? No. We're as real as anything can be. The holographic principle doesn't say we don't exist. It says the description of our existence can be equivalently given in terms of a lower dimensional theory. We exist. We're just not what we intuitively think we are. We're not three-dimensional collections of particles. We're patterns of information that manifest three-dimensional structure that's still real, still physical, just different from the naive picture. Some people confuse the holographic principle with simulation theory, the idea that we might be living in a computer simulation. These are different. Simulation theory says some external intelligence created our universe as a computation. The holographic principle says our universe's physics can be described by a lower dimensional quantum theory. It's not about someone simulating us. It's about the mathematical structure of physical law. Though I'll admit, the line between these ideas can blur. If the universe is fundamentally computational, if it's quantum information processing, then in some sense it is a simulation, not created by someone else, but self-simulating, computing its own existence through the laws of quantum mechanics. Let me tell you about recent developments. In the last decade, physicists have found more evidence for holography beyond AD-CFT. The firewall paradox, proposed in 2012, suggested contradictions in the black hole complementarity picture. But subsequent work has shown that holography, when properly understood with quantum error correction, resolves these paradoxes. The ER equals EPR conjecture, proposed by myself and Juan Maldacena, suggests that quantum entanglement creates wormholes in spacetime. Entangled particles are connected by Einstein-Rosen bridges, wormholes. This deepens the connection between quantum information and spacetime geometry. It suggests that space itself is a network of entanglement, a web of quantum correlations. Physicists are also applying holographic ideas to condensed matter physics, to understand exotic materials and phase transitions, to quantum information theory, to understand how information is stored and processed in quantum systems, to cosmology, to understand the early universe and inflation. Holography is becoming a unifying framework across physics. It's not just about black holes and quantum gravity. It's a principle that might apply everywhere. And here's what keeps me up at night. If the universe is holographic, what is the boundary? For AD-CFT, the boundary is clearly defined, but for our universe, what plays that role? Is it the cosmic horizon? Is it something more abstract? We don't know yet. We're still working out the details of de Sitter holography, the holographic description of a universe like ours with positive cosmological constant. And there's a deeper question. If space is emergent from entanglement, what about time? Is time also emergent? Many physicists suspect it is. At the most fundamental level, perhaps there is no time. Only timeless quantum correlations that create the illusion of temporal flow in certain limits. This is speculative, but motivated by the holographic principle. If space isn't fundamental, maybe time isn't either. Maybe both are emergent features of quantum information organizing itself. This would be the ultimate revolution. Not just space, but space-time itself as an emergent phenomenon. We're not there yet, but the holographic principle points in that direction. Let me end with this. The holographic principle is not just an interesting mathematical curiosity. It's a profound statement about the nature of reality. It says the universe has one less dimension than it appears to have, that three-dimensional space is a projection from a two-dimensional boundary, that space-time is emergent from quantum entanglement, that information is conserved in black holes, that the universe has a finite information content. All of this comes from trying to understand how quantum mechanics and gravity fit together. And the answer is holography. After 50 years of thinking about physics, this is the most radical idea I've encountered. The universe is a hologram. You are a hologram. Three-dimensional space is an illusion, a projection of information from a lower dimensional surface. This is what quantum gravity teaches us. This is what the mathematics demands. And this is what I believe is true. The universe is a hologram. Thank you for watching. Welcome to holography.